Good nights, my dear friends. My name is Richard. Find a quiet place. Let your body rest. Feel the bed beneath you, holding you softly. Close your eyes. Slow your breath. Tonight, we drift through galaxies, past dying stars and glowing gas, past the edge of what we know, and into the heart of the black hole. This is not a story of fear. This is a journey of awe. A bedtime lecture about gravity's secret, Einstein's dreams, and the strange silence where time comes undone. The story is waiting. When you're ready, we'll begin. Somewhere in our galaxy, at some time in the future, a spacecraft from Earth will encounter the most dangerous object in the universe. This is an object that is not made from ordinary matter. It's not made from antimatter. It isn't made of matter at all. It's made out of a pure warpage of space and time. Nothing comes out of it. Things only go into it. It's that one-way nature which probably upsets people most, causes them to be really disturbed. And in fact, causes many scientists to be disturbed. That's why it was quite surprising when astronomers found that there was really good reason to suspect that the universe should be full of these extraordinary objects. At some time in the future, a spacecraft from Earth will encounter an extraordinary universe full of black holes. Everybody has heard of black holes. No one has really seen them. The spacecraft of our dreams has reached not a solid object with the boundary to a region of space where gravity has gone mad. Waiting below is a black hole in space. Welcome to the edge of the universe and to the end of space and time. Phil Charles not only dreams black holes, he hunts them down for a living. He's found the strongest evidence yet for a black hole lurking in our own galactic backyard. Searching for these things is the most wonderful way of going to the frontiers of modern physics. The most exciting thing that a modern scientist can do. Pulled up the spectra using FIG, and that was by day Phil Charles lectures on astrophysical theory at Oxford University. Only visible from the Southern chemistry. By night he is at the forefront of the hunt for astrophysical facts. To be a successful black hole hunter, you have to have ready access to the largest ground-based telescopes. Around the globe, Phil Charles and his fellow astronomers call upon the world's most sophisticated astronomical arsenal to probe the depths of space for these mystery objects. From X-ray satellites and the Hubble Space Telescope in orbit, to the finest radio and optical telescopes on the ground. If you imagine you have a black hole and material is falling into it only in the 1992nd, has mainstream science come to a consensus that black holes might actually exist. Gravitational collapse theory tells us that deep inside black holes, everything we know about the universe will come to an end. When a massive star dies, it will have no choice but to form a black hole. For astronomers like Phil Charles, black holes remain the big game of the universe. But how do you catch a small, invisible nothing that may be hundreds or thousands of light years away across the noisy ocean of space, with more stars in the heavens than all the great veins of sand on all the worlds? Beaches? How do you hunt for that one dark star that swallows light rather than shines like a beacon? Astronomers must hunt not for black holes themselves, but for the effects they generate in space around them. Phil Charles looks for visible stars that black holes might have trapped in orbit. That we do through the fact that in the late 1982, the Japanese launched an X-ray satellite called Dinga, which had what we call an all-sky monitor on it for detecting X-rays from anywhere in the sky. While sweeping the heavens in 1989, the Jenga satellite reported a mysterious burst of X-rays in our own galactic neighborhood. The source of the radiation was an invisible object, 3,000 light-years away, around which a faint star seemed to be circling. The star had the catalog name V404 Cygni. It was just the star Phil Charles had been looking. Phil Charles' prime weapon in the search for black holes is the massive William Herschel telescope, perched on the rim of an extinct volcano 2 kilometers above the Atlantic Ocean. For the last 7 years, Charles has pointed the telescope towards the star V404, trying to work out just what sort of highly compact object the star must be circling. The most likely candidate is a stellar mass black hole, the most common kind. According to the theory, such a black hole should weigh 10 times as much as a star like our Sun, but would only be about the diameter of central London. Less common is a second type of black hole, supermassive heavyweights, believed to lurk in the heart of galaxies. But to understand any black hole, you must begin with gravity. For within this darkness, gravity is in total control. Our modern quest to understand gravity and ultimately black holes was born in this room on Christmas Day 1642. But it was a shaky start. The great Isaac Newton was premature and only just survived his first day of life. Showing little promise as a farmer, the young Isaac Newton was sent up to Cambridge. Newton would formulate laws of physics, which still form the basis of modern science. Fate played its part. In 1665, the plague swept across England. Cambridge was closed to help contain the spread of the contagion. Newton was forced to flee. He sought refuge back at Westhorpe Manor. Over the next 18 months here, he was to discover the mathematics of calculus, to formulate laws for the motion of the planets, and to unravel the spectral nature of light. And one day, a falling apple interrupted his thoughts and led him to ponder gravity itself. Newton was the first person to give us a really detailed mathematical understanding of one of the basic forces of nature. And of course, it was the first great triumph of mathematical physics. He told us that the force which holds us down here on the Earth, and which allows an apple to fall, is the same force which holds the Moon in its orbit around the Earth and makes the planets move in their courses. Newton reasoned that all matter in the universe has gravity, that it's a force that reaches out from one body to another and pulls everything inwards. The more mass an object has, the more gravity. the stronger this inward pull. The first person to combine this notion of the inward pull of gravity with knowledge that the speed of light was finite was John Michell. As rector of Thornhill Church in Yorkshire, and one of the 18th century's great forgotten scientists, Michell took Newton's view of gravity to its ultimate dark conclusion. Mitchell's giant leap was to imagine a ray of light leaving a star in the same way we think today of a rocket leaving a planet. To escape the Earth's gravitational pull entirely and travel into space, a rocket needs to push itself upwards at 11 kilometers per second, faster than gravity tries to pull it back down. Michell knew nothing of rockets to the moon, but he did know that in theory, a massive star could have so much gravity that it would pull back into its clutches even rays of light, traveling at 300,000 kilometers per second. John Michell worked out that if you had a body weighing about 100 million times as much as the sun, light couldn't even escape from it. And he then went on to say that for that reason, maybe the most massive objects in the universe might be invisible to us. Michell had explained how gravity could turn a star black, but not how it could turn it into a hole. A complete understanding of the life and death of stars awaited the nuclear age. Every star we see in the heavens has a giant nuclear reaction raging at its core. It's what makes a star, like our own sunshine, so hot and bright. It's a precarious balance that gravity will always win in the end. When the sun runs out of nuclear fuel, its own gravity will crush it into a tiny ball the size of the Earth, but a 1,000,000 times more dense. But our sun has too little mass and therefore too little gravity to become a black hole. Instead, astronomers call such a feeble ember a white dwarf. But when a giant star switches off, it goes with a bang. While we see the outward explosion as a supernova, this masks the implosion going on inside. The core has been given a gravity bear hug so extreme that all the atoms have been squeezed into a ball of super-dense subatomic particles called neutrons. We know that there are neutron stars which are just a little bit heavier. And the question is, what do you have beyond that? We believe it's black holes. Theory suggests that when a neutron star is more than 3 times as heavy as our sun, even the neutrons cannot resist gravity. The collapse is irrevocable. The density of mass becomes so great in the center that gravity overwhelms space itself, distorting it so horribly that it and time with it begins to wrench off from the outside universe. A darkness forms at the heart of the collapsing star and moves relentlessly outwards as the star's brilliance is sucked in. As the star dies, a black hole is born. Just how a black hole can manifest itself so powerfully in the emptiness of space is something that weighs heavily on Professor Stephen Hawking. Born exactly 300 years after Isaac Newton, Hawking now holds Newton's old job at Cambridge University. Hawking's mind roams free not in Newton's universe, but in the universe of Albert Einstein. We are used to thinking of GRA as a force that pulls bodies towards the Earth and pulls the Earth towards the Sunday. But Einstein had the brilliant idea that gravity could be caused by space and time being curved rather than flat. Einstein realized that nothing can exist at a point in space without existing at a particular time as well. Space and time seem to be woven together to form the flexible four-dimensional fabric of the universe, so-called space-time. Space-time is almost impossible to contemplate because our entire sensory existence is limited to the three dimensions of everyday experience. If space-time were empty, the sheet would be flat. But massive bodies like the Earth and Sun will bend the sheet and cause it to be curve. This curvature is Einstein's concept of gravity. The more mass a star or planet has, the more steeply it bends space-time around it, and so, the more gravity it has. Throw something extremely heavy like a collapsing star onto the sheet, and you soon end up with a universe full of holes. Things can fall into a black hole, but nothing can get out. Everything that has ever fallen into the hole is destroyed at the singularity. All that remains in the outside universe is a perfect sphere of absolute darkness, a gravitational ghost of the star that died. This sphere is called the event horizon, and it marks the edge of the abyss. It's just a location. It is that unique location where gravity becomes so strong just inside there that nothing can escape. While the event horizon may be only a few kilometers in diameter, the immense gravity of the singularity will have sucked a hole inside it that is impossibly deep to measure. In the center there is the so-called singularity, which is a place where, according to Einstein's theory, everything goes infinite. Where if you do calculations, as it were, the smoke pours out the computer and something goes wrong. Astronomer Phil Charles thinks he has proof that such intangible objects are to be found in the real universe. The giveaway signal was the sudden burst of unexplained X-rays which alerted Phil to V404, the faint star trapped in orbit around an invisible compact object. These are signatures of a star not much different from the Sun, and it represents more than 80% of the light here that we can follow and use the speeds that we measured to determine the mass of the object we cannot see. An excellent analogy is that of a big, strong man and a very small, light woman. As they swing each other around, the man hardly moves, and the woman, just by the balance of their weights, moves much more. Calculations show that V404 orbits have heavy, mysterious partner once every 6.5 days. To achieve speeds like these, the partner must be very heavy indeed. The mass that we measure by this process is 12 solar masses, 12 times the mass of the Sunday. That means it is substantially heavier than what we think is the largest mass of a neutron star. The black hole has embraced V404 a deadly dance, ripping gas from the hapless star and feeding it into a great disk of cannibalized matter. As this material spirals towards the hole, it heats up and sends a last desperate X-ray signal to the outside world. Nearly a dozen similar objects have now had their presence betrayed to astronomers in the same way by X-ray signals. One of the first was signal X1. When Hawking and Thorne made the bet in 1974, the evidence was thin. But as the years rolled on and the evidence mounted, Hawking felt it was safe to concede the wager. This handwritten bet has come to symbolize the first real acknowledgement by the scientific establishment that black holes are really out there. Already, robot spacecraft have explored the planets. Someday we may send an intelligent probe to a black hole in the depths of space beyond. Our mothership travels fast enough to insert into a safe orbit around the hole. A different fate awaits the probe. As you approach a black hole, that difference in pull becomes larger and larger. As you get closer to the center, gravity will get more extreme. You would be squeezed and distorted. Spaghettification is the name some people use for this experience. Spaghettification is an experience nothing can survive. The fragments streep down and into the blackness of the hole. You are falling into the black hole. Will get stretched, and our bodies will get mutilated before we even reach the horizon. Something else strange happens well before the event. Horizon is crossed. Not only space is being stretched, so is time. The closer the probe gets to the event horizon, the harder light from it struggles to escape. The mothership sees the probe slow down until it seems to stop. Time doesn't change for the probe because gravity is stretching its whole existence. But from the mothership's perspective, the probe has become frozen in time. It is both destroyed in an instant and hovering for eternity, depending on your point of view. We don't really know exactly what would happen deep inside a black hole. If you were to fall directly in, it could be that something even stranger happens to space under these conditions, something like what happened at the beginning of the universe, and indeed some people have speculated that in general it may be possible to avoid the complete singularity and emerge somewhere else. A movie in which at the end of the film the spaceship goes inside the black hole and comes out the other side into another universe. That don't happen. It just doesn't happen at all. The fundamental laws of physics say that at the center of the black hole there is a singularity, a region where space and time are infinitely warped, a region where when matter flows into it, matter gets destroyed. Speculation that tamed black holes may provide a way of cheating the laws of physics have become a hallmark of science fiction. Physicist Igor Novikov likes to speculate on what would happen if you join two black holes together to make a wormhole. Wormholes are real bizarre objects. We can imagine a wormhole as two holes and some kind of a tunnel between them. But this tunnel is not in our space, and it is in some kind of hyperspace outside of our dimensions. To make such a wormhole, we would have to engineer space-time. First, bend it until it begins to form a black hole. But not so much that a singularity is born. Then join the bottom of this gravity tunnel to the bottom of a second tunnel to make two holes connected by a continuous tube through hyperspace. Step 2 would be to move one hole to wherever it was you wanted to travel. One of them can be near our Earth, another in another galaxy. But this tunnel can be extremely short, say a few meters. The tunnel would also be very fragile, prone to collapse as soon as a traveler attempted to pass through it. But if we could develop the technology to tame the ferocious forces at work, we would have opened an interstellar shortcut. Where a black hole is a one-way street with a dead end of the singularity, a wormhole could be a freeway to the stars. Oxford University's Roger Penrose pushes the mathematics of black hole in a different direction. He's formulated a way to extract enormous quantities of energy from the way black holes spin at the same time as sending enormous quantities of garbage to oblivion. In the real universe, most black holes should spin because the stars that formed them would have been spinning as they collapsed. Their massive gravity swirling the fabric of space around them like water around whirlpool. Penrose's energy extraction process would require building a power station at a safe distance around the spinning hole. You could imagine firing a lot of particles or bodies into the neighborhood of the spinning hole in the right direction. The forces of spaghettification will rip these particles apart. The particles could be any old rubbish you never wanted to see again. Half would disappear into the hole, half would be flung outwards with a slingshot of gravitational energy that could be used to drive a turbine. The source of that energy isn't the slowing down of the black hole's rotation, because as these particles keep falling into the hole, they gradually slow it down. But since there's usually an enormous amount of rotational energy in a rotating black hole, this would be an extraordinarily efficient way of extracting energy. But there is a long way to go before observational science catches up with the wilder speculations of black hole theory. Another country, another telescope. The hunt takes Phil Charles to Australia. The Australia has access to the southern hemisphere of the sky, and there we can see the Magellanic Clouds. And the large Magellanic Cloud is our nearest neighboring galaxy. And there are about half a dozen very interesting compact objects that we want to study from here. We need to get maybe 20 or 30 so that you can really see the population of black holes that we're looking at. Do they all have similar masses? Are they a spread of mass? Do they all come from the same kinds of original stars? We can start to work that out once we can get enough of them. While Phil Charles turns his sights on the stars of our neighboring galaxy, other astronomers are probing galaxies further afield. Here they are finding objects of staggering immensity, formed not from the death of a single star, but from the collapse of enough matter to make millions. Such objects astronomers now believe are supermassive black holes. Ever since radio telescopes began, EVs dropping on the heavens, the strongest and most puzzling signals have come from the hearts of distant galaxies. Astronomers now suspect these radio signals are generated by central supermassive black holes. Mighty jets of energized particles are blasted into space from an invisible engine that drives these so-called radio-G galaxies like great wheels through the heavens. Nameless stars are ripped apart by an immense gravity to feed central disks of white-hot matter, shining 100 times more brightly than a whole galaxy of stars like our Milky Way. Powering everything is the hidden central object as small as our solar system. But enough matter to make millions or even billions of stars has undergone a titanic gravitational collapse. M87 jet is like an enormous death ray of charged particles moving close to the speed of light and 6,000 light-years in length. The jet is a signature of the way the black hole is swirling matter and space around it. Astronomers use the speed of the swirling matter to calculate the black hole's mass. Astronomers suspect radio galaxies are those galaxies with plenty of matter left for the black hole to eat. If a galaxy appears quiet, it's probably because the black hole has run out of food. but seeing them is still. Beyond us, even the latest high-resolution Hubble images can show only the bright central disk. The jets of energized particles, but not the black speck in the middle. We will never be able to appreciate the full majesty of a supermassive black hole from Earth. Time for our spacecraft to make another journey. If one was to take a journey starting in the outer part of a galaxy and moving in, see very hot glowing gas filling the galaxy, which is being heated by some mysterious, powerful central source, you would find gas orbiting in a disk, swirling at nearly the speed of lights, and getting very hot. Getting so hot that it radiates not just visible lights, but very energetic radiation like X-rays. It is one of the great cosmological contradictions that the larger the black hole, the weaker the gravitational forces near the event horizon. This time there is no spaghetti. As we approach the event horizon, the intense gravitational curvature wrenches the light from the universe to a bright point directly overhead. We have reached the point of no return. We are now inside the black hole. But where is the singularity? If you were falling into a black hole and the singularity, you knew from your calculations that the singularity was out there, and you're heading for it. You look at it. You don't see it. It's like a singularity that you're hitting for in the future, and you don't actually see. The singularity is where science ends and speculation begin. Space and time have ceased to exist, replaced by a seething, chaotic mass we can call quantum foam. Into this bizarre conjecture has disappeared all the mass and energy that has ever fallen inside the event horizon. This is where Einstein's laws fail. This is where the laws of quantum mechanics fail. This is where the secrets of the universe are hidden. The singularity is an object at the core of a black hole that is governed not by the ordinary laws of physics that we're familiar with, but by the laws of quantum gravity, which we only are beginning to glimpse and understand. If the probe was strong enough, it would fall towards the singularity for perhaps an hour, until it blindly met its future at the end of space and time. What really happens at the end? As unknown as what happened before the Big Bang. It's the other end of that story. And so, we drift now beyond the edge of gravity's reach. Past the swirling stars, the jets of fire, and the quiet hunger of collapsed light. Behind us, galaxies turn slowly in the deep, like ancient lanterns burning through time. The black holes remain, silent, invisible, vast. Not monsters, but windows. Not destroyers, but keepers of the universe's most guarded secrets. What lies inside, we may never fully know. But tonight, we've come closer. We've looked into the abyss and found not fear, but wonder. And let your dreams carry you across the curve of space and time. Good night.